Chapter 2 of Fiber Optic Communications. This is Transmission Concepts and Communication Fundamentals. In this chapter, we will understand modulation and multiplexing techniques used for transmission in fiber optic systems, such as on-off intensity modulation and wavelength division multiplexing. Chapter objectives are: we will list the different types of transmission channels, discuss analog to digital conversion, explain frequency, phase, and amplitude shift keying, as well as on-off intensity modulation. Explain multiplexing techniques. Those techniques are frequency, time, and wavelength division multiplexing, including coarse wavelength division multiplexing and dense wavelength division multiplexing. And calculate the bit rate of a T1 carrier system. Describe North American digital hierarchy. Describe the SONET system and its relationship with the T carrier system. The path where a signal is transmitted from one point to another in a communication system is a transmission channel. It's also referred to as a communication channel. Bandwidth is one relevant characteristic to a transmission channel. There's two different types of bandwidth. When we're talking about analog bandwidth, this is the measured range of frequencies a channel can carry. It's measured in hertz. We're talking about a digital bandwidth. This is the rate of data transfer through the channel. This is measured in bits per second. Multiplexing is separating the transmission medium virtually so that you have several communication channels so that many independent signals occupying smaller bandwidth can be transmitted at the same time. You're combining multiple signals onto one transmission channel. Voice channels are 4K for analog and 64K or kilobits for your digital channels. Video channels are 6 megahertz or were 6 megahertz. These are the older UHF, VHF television channels. We also have digital video channels ranging from 4.85 megabits for standard definition to 19.39 megabits for high definition television. And data channels. These are channels carrying a digital signal. Digital bandwidth is measured in bits per second, depends on the type of signal it carries. So it depends on whether it's carrying voice, video, or data. To increase the amount of information a system can carry and to reduce the cost, the vast majority of telecommunication systems today are designed to transmit digital signals. Any type of signal that is analog in nature, like a voice signal, is first converted into its digital counterpart and then transmitted over a data channel. An analog signal can always be converted into a digital signal through analog to digital or A to D or ADC conversion. There are 3 steps in this conversion. The first step is sampling, and that's taking a sample at certain points along a analog voice signal. So every 125 microseconds a sample is taken. The analog signal is sampled at specific intervals, 125 microseconds. The result is a series of pulses with an amplitude equal to the value of the analog samples at that instant in time. So you have, for an analog signal, you have a constant change in the value of that voice or the level of that voice, but we're only sampling at these specific points, so every 125 microns. And what that gives us is something that looks about like this for our samples here as the frequency of that analog signal goes up and down. Sampling step is also called a pulse amplitude modulation. Next step is quantization. Because we only have set values that we can transmit or set values that we want to transmit, and this helps keep down the amount of data that these analog signals are going to take up, we need to round up or round down or truncate these samples to their nearest predetermined values. So each sample of the original signal is approximated to the nearest value of a discrete set of numbers. In this case, we're using 256 quantization levels. Some samples are rounded up and others are truncated. The third step is encoding. An 8-bit binary string is assigned to each approximated sample. With 8 bits, we can represent 256 quantized levels. So when we're talking about binary, we've got an 8-bit word, and each different number, each different 8-bit number corresponds to a level or a predetermined level on our sample, and those are going to be transmitted in binary code. When we combine quantization and encoding, this is pulse code modulation. So we go through sampling or pulse amplitude modulation, and then we go through quantization. This gives a predetermined value, and then we encode and then transmit those encoded words. Quantization and encoding are pulse code modulation. That binary stream is sent toward our transmitter. For modulation, modulation is the process of changing one property of a high frequency sine wave, called a carrier wave, according to the signal carrying the information. So modulating or changing that signal to represent the data that we want it to pass. Modulation changes or increases the frequency of the signal, so the frequency content falls within the bandwidth of the transmission medium of choice. We also shift the signals so that several signals transmitted at the same time don't overlap and don't interfere with each other. This allows us to put multiple signals on the same transmission line. There's different modulation techniques. The two main ones or the two categories are analog modulation and digital modulation. Analog modulation would be changing a voice signal or changing the frequency of an analog signal. One current example of that, or one more recent example of that, would be auto-tuning voices, where an audio specialist would mix in other sounds to voices. Another one is, and the other side of that is digital modulation. That's performed by digitally modulating these signals. So digitally modulating a voice signal. Fiber optic systems or fiber optic communications is digital, so we need to use digital modulation techniques. Frequency shift and phase shift keying. One frequency for the 1 bit and a different frequency for the bit 0. So you can see here we have our carrier sine wave or carrier signal, and then here we have our modulated signal. So for a 1, our signal remains unchanged, and for a 0, we're decreasing the frequency of that signal. And then when we go back from a 0 to a 1, we're returning that signal to its carrier wave. Limitations on this, or the cons on this, we've got speed limitation and bandwidth constraints. You can't send as much information as fast when you're modulating a signal like this, because it takes time to change that carrier signal. Another type that we have is a phase shift key. The phase of the carrier wave is shifted when the bit changes. So we have our carrier wave again, and then for a 1, our carrier wave remains in phase, or our data modulated signal remains in phase. And when we switch to a 0, you can see here there's a change in the phase. So instead of this signal going up and continuing on its upward stroke, we've modulated it. We know it's a 0 because that signal is going down. In this example, we're using 2 phases, so they're 180 degrees out, but you also have quadrature and 8 level phase shift keying, where you would have every 90 degrees for quadrature or every 45 degrees for an 8-part signal. Then we have amplitude shift keying. You have 1 amplitude for a 1, and that's going to be your carrier signal for a 1, and then for a 0, we decrease the power, we decrease the strength of that signal. And finally, what we use most commonly with fiber optics is on-off intensity modulation. It's where a light pulse is transmitted when the source is turned on, no light pulse is transmitted when the source is turned off. So for a 1, we have a pulse. For a 0, we have no pulse. This type of modulation is widely used for fiber optic systems. Pulses of light represent 1s. There's also reverse reverse modulation where a pulse would equal a 0 and a 0 would equal, or 0 would be represented by a pulse, but not many systems use those. We have direct modulation. A modulator is a device that converts electromagnetic signal into a light pulse. Indirect modulation, an LED or laser diode produces intensity modulated light pulses by directly coupling the data bit stream to the drive circuit of the diode. You can get very high data rates with this, up to gigabits with this, and it's just turning the light on and off. Requires a large channel bandwidth due to chirping. Chirping is when we move our center wavelength from 850 nanometers or 1300 nanometers, when that center wavelength is shifting to 840 or 855. And that happens because we're turning on and off that light. It's similar to turning on and off a light switch. Over time, there's going to be some wear on that laser diode or on that LED that causes the center wavelength of the light generated to be changed. For external modulation, we're using a continuous wave, so you have no chirping because it's always on. This light is always on. Externally controlled electric fields are used to change the refractive index of an external modulator made of lithium niobate. You have a continuous light traveling through this material, and that light is going to undergo phase and amplitude changes that turn on and off the light. So external modulation creates a lot less chirping than direct modulation, so it's going to be good for long haul and high-speed data communications. But high data rates require stable laser drive currents, and these laser drive currents are created, or these stable laser drive currents are created by very expensive components that go into power conditioners. We have, inside of our fiber optic systems, we have 4 basic components. You have a transmitter and a receiver. The transmitter is going to convert electrical pulses into a light pulse and transmits them down the fiber. Your transmitter contains your light source. Receiver receives and demodulates the light pulses back into electrical pulses. This is going to receive or contain a light detector. Between those, we have the optical fiber and connectors. The optical fiber is your transportation medium, going from transmitter to receiver, and your connectors connect those optical fibers to the transmitter and receiver. Multiplexing. Multiplexing is a process of combining several signals in order to efficiently use the available bandwidth of the communication channel. Multiplexing is taking multiple signals and putting them down one communication channel. Demultiplexing is done on the far side, on the receive side, and that's splitting those signals back up into their independent signals. There are different types of multiplexing. We have frequency division multiplexing. It's considered an analog type of multiplexing because it's performed on analog signals. You can't use this in fiber optic signals. And we have time division multiplexing. Time division multiplexing is a digital type of multiplexing because it's performed on digital signals. TDM can be carried on your SONET and then transmitted over a fiber optic system. We also have wavelength division multiplexing. This is the type of multiplexing that we use for fiber optic systems. For time division multiplexing, it's a digital type of multiplexing because it's performed on digital signals. Generally has 24 channels to multiplex 24 voice signals, and we use that time frame of 125 microseconds divided into 24 time slots. Each digital signal is assigned to a channel made of an ordered sequence of time slots. So if we have 24 time frames, they could each go to their own individual voice channels, but in this case we're showing that we only have 3 voice channels, and so each of the 24 time slots are being broken up among those 3 voice signals. Different signals take turns during the transmission on the same link. This is only 125 microseconds for each signal, so they're transmitting their information during their predetermined time slots. For wavelength division multiplexing, we have 4 independent bit streams converted into light pulses and combined to be transmitted simultaneously over single mode optical fiber. So we have our bit streams here, and they're each going into their own transmitter, or each going into their own modulator. And then they're going to go through a series of lenses that combine them and send them down the same fiber optic transmission line. So this gives us, rather than splitting up each of these signals and giving them each 2.5 gigabytes or 2.5 gigabits, we're combining all 4 of them and we're creating a 40 gigabit line. In dense wavelength division multiplexing, we can have up to 160 wavelengths transmitted simultaneously. Each wavelength is going to be spaced by about 0.8 nanometers, and the center wavelength on these is 1550 nanometers. These are pretty significantly more expensive than coarse wavelength systems, and they're used for very long haul transmissions. Coarse wavelength division multiplexing, you can have a maximum of 18 different wavelengths. Typically what you're going to see is 4 to 8 different wavelengths, and they're spread by 20 nanometer wavelength spreading, and that's going to be between 1470 and 1610 nanometers. These are used on television networks and over shorter distances. They're less expensive because you don't have to have as finely tuned laser diodes as you would with dense wavelength division multiplexing. The T1 carrier. T1 carrier is a standard of digital transmission based on TDM multiplexing. T1 carrier is composed of 24 digital voice channels and carries up to 24 digitized voice signals, multiplexed by means of time division multiplexing. To calculate the bit rate, we have 8,000 samples per second and 24 time slots per channel, plus 1 framing bit, or 1 bit telling it that this is our frame. This is where our signal ends, so that a new time frame begins. 1 time slot is 8 bits. So we have 24 time slots times 8 plus 1 is 193 bits per frame. We have 8,000 frames times our 193 bits, or 8,000 bits times our 193 frames gives us 1.544 million bits per second, or 1.544 megabits. This is what our North American digital hierarchy looks like. North American digital hierarchy is a set of transmission speeds arranged to multiplex higher numbers of signals based on the T1 carrier. So our T1 carrier is a digital signal level of 1, has 24 voice channels. It is 1 T1, and the transmission rate is 1.544 megabits. Our bit width in nanoseconds is 647.7 nanoseconds. To maintain synchronization, we add extra bits. This is called bit stuffing. That's why each of these, as they progress, is not a multiple of the T1 or a direct multiple of 1.544 megabits. Our hierarchy here, this is an example of a T1 carrier system structure. Our T1s feed into T2s, T2s feed into T3s, and so on until we get up to our maximum. SONET is a more recent hierarchy, or a more recent network structure. It's designed to be compatible with older T-carrier systems and is still based on that same 125 microsecond time period. It allows transmission of signals of different nature, such as voice, audio, video, and data at a much higher rate. And if you look here, our OC1 level has 672 voice channels. That's compatible with our T3 carrier, which has 672 voice channels. Synchronization is reached by using an atomic clock as a timing reference, thus eliminating the necessity of variable length bit stuffing. We don't have to add those extra bits in for our SONET because they all draw their time from the same clock. So our SONET bit structure, we have our T1 lines feeding into our OC lines, or feeding up to our OC lines. Once we get up to a T3, then we can start feeding into OC 1, 3, 12, 48, up to OC 678. Chapter summary. We listed the different types of transmission channels, discussed analog to digital conversion, explained frequency, phase, and analog shift keying, as well as on-off intensity modulation techniques, explained multiplexing techniques. Those are, again, frequency division, time division, wavelength division, coarse wavelength division, and dense wavelength division multiplexing. Calculated the bit rate of a T1 carrier system, described the North American digital hierarchy, described the SONET system and its relationship with the T carrier system. And if you have any questions, please email me.